Welcome to this video. My name is Mark Scythian. The date today is July 11th, 2024. So this video is going to focus on the Oxy-Hydro Rocket Motor. This is a certain rocket and payload assembly and its propulsion system, powered by the mixture of liquid hydrogen in one fuel payload combined with liquid oxygen on another partial payload. So there is the pre-ignition phase of launch. So you can notice these small diameter lines are going to deliver a stoichiometric balance of liquid hydrogen and oxygen mixture. And note that the liquid oxygen will vaporize into a pure gas of oxygen gas to supersede the oxygen in the atmosphere, which is only 21% by composition. Our air, or our atmosphere, is 78% nitrogen, 21% oxygen in their gaseous state, and then 1% various and numerous inert gases. So if we take a combustible substance with the lowest molar mass, this is the hydrogen or the liquid hydrogen, and instead we burn or combust the liquid hydrogen in 100% oxygen mixture combustion, we are then going to optimize the delivery of kinetic energy in the form of thermal kinetic energy. So that's the pre-ignition light off, these small diameter lines. And so your combustion starts, the turbine stack, which converts the thermal kinetic energy into mechanical energy or mechanical power. So this would be the input side of the pre-ignition light off without the diverter cone. And so this turbine would rotate and then drive a high horsepower Oxy-Hydro fuel pump. We'll say on a modern rocket it may be as highly rated as 100,000 mechanical horsepower to drive the primary oxy-hydrogen fuel pumps or pump to then discharge the large mass flow hydrogen-oxygen mixture, which then culminates in the divergent-convergent combustion chamber with then a divergent exhaust nozzle rather than a choked convergent nozzle, it being a sonic nozzle assembly. So this then allows supersonic gas flow to discharge at or above the speed of sound. When this occurs, Bernoulli's principle reverses itself. So what we would have with an augmenting or divergent nozzle, instead of decreasing the velocity and increasing the pressure at Mach 1 or greater, this divergent sonic nozzle will instead increase the velocity. So without a sonic nozzle or a standard choke nozzle that has a convergent nozzle exhaust, it is not possible to discharge a fluid at supersonic flows. Hence the term sonic nozzle, as opposed to the subsonic nozzle or the choke nozzle. That's the whole principle of the rocket motor, is to have pre-ignition combustion to drive a turbine, which then drives a high horsepower fuel pump assembly. Now, an even simpler, more practical and powerful method was to just get rid of this hydrogen and replace it with kerosene jet fuel, which is a derivative of diesel with fewer lubricants, and then ignite the kerosene jet fuel within a 100% oxygen combustion environment. There are other methods to increase thrust, including the injection of aluminum slag particles. Force thrust is mass times acceleration. So if there's a way to articulate an increase of mass without disrupting flow, that was one of several methods to increase the thrust output, to inject temporary aluminum slag particulates. But practically speaking, if we revert to the Saturn and Apollo rockets, they were the mixture of kerosene and pure oxygen. So again, the summary is that the turbine-driven fuel pump is powered by the pre-light-off phase, and after the combustion takes off, we then have a standby system which permits a greater horsepower and reflow to drive these turbines and increase the amount of fuel delivery. So we think of fuel pumps as being a constant flow system, or something that we might take for granted as just turn the pump on and fire the system up. But when you're dealing with power plants that are high performance, a challenge is to increase the propulsion power or horsepower, is the challenge of how much fuel can you actually deliver into the system. And then it becomes a high mechanical power application requiring the partial combustion itself to actually develop enough horsepower to deliver the fuel load. So that is the whole principle of the rocket motor, using the combustion process itself to increase the amount of fuel flow to the primary combustion chamber and exhaust nozzle designed for supersonic applications, hence a sonic nozzle. So the last point is, if you were discharging a high pressure gas or liquid reservoir, we'll say just a gas reservoir for simplicity, such as a compressed air tank, you could do the Bernoulli equation and calculate theoretically that the compressed air nozzle, which is very convergent, a very choked compressed air nozzle, the equation would reveal a supersonic velocity output for the V2 from the V1 as 0. However, in the real world, when you actually do discharge that theoretically supersonic velocity out of a choke nozzle, it will slow down and only reach at the most Mach 0.99. So this is a function of the speed of sound equation, which is simply just the Rankine absolute temperature of the air, Fahrenheit plus 460, its square root, then multiply times 49.022 to calculate the speed of sound in feet per second. So we have an issue that the speed of sound will increase as temperature goes up, but we don't really have that issue when discharging high pressure compressed air out of a choked air nozzle. So you repeat the experiment and you see that a choked nozzle or subsonic nozzle, even with a sufficient potential energy pressure, will not allow a supersonic discharge of air, or in this case a gas. And that is because the nozzle is not reversing its geometry consistent with the inverse function of Bernoulli's equation at or above the speed of sound. So actually this divergent sonic nozzle is increasing its velocity at the speed of sound or greater. So once the choke nozzle is removed and a sonic nozzle is replaced, then you will incur a supersonic gas velocity out of that compressed air tank. So there are limitations, such as the air molecules literally coming to a rest at the surface. So its boundary layer is going to then increase its speed and break a sound barrier down to the molecular level. So this is important to understand, because if you're working with rocket motor and rocket propulsion, you now have a substantial increase in the speed of sound because the temperature of the gas with respect to the atmosphere is also substantially higher. So these are basic fundamentals that support rocket propulsion and rocket propulsion power plants and or motors. Thank you for watching this video and have a great day.